Closed loop control of an induction motor. A closed loop control is normally required in order to satisfy the steady state and transient performance specifications of AC drive. The control strategy can be implemented by the first one, scalar control, where the control variables are DC quantities and only their magnitudes are controlled. Then second one, the vector control, where both the magnitude and phase of the control variables are controlled. Third one, adaptive control, where the parameters of controller are continuously varied to adapt to the variations of output variables. The dynamic model of an induction motor differs significantly from that what we studied in the previous topics, and it is more complex than the DC motor. The design of feedback loop parameter requires complete analysis and simulation of entire drive. Some of the basic scalar feedback techniques are discussed in this video. A control system is generally characterized by the hierarchy of the control loops, where the outer loop controls the inner loop. The inner loops are designed to execute progressively faster. The loops are normally designed to have limited command execution. This is an arrangement for stator voltage control of an induction motor by AC voltage controller at a fixed frequency. The speed controller K1 processes the speed error and generates the reference current IS reference. And K2 is the current controller, and K3 generates the delay angle of the thyristor converter, and the inner current limits the loop sets the torque limit indirectly. The current limiter instead of current clamping has the advantage of feedback the short-circuited current in case of fault. The speed controller K1 may be a simple gain, that is proportional type, or proportional integral type, or lead lag compensator. This type of control is characterized by poor dynamic and static performance and is generally used in fans, pumps, and blower drives. This is an arrangement for volt hedge control with addition of controlled rectifier and a DC voltage control loop as shown here. After the current limiter, the same signal generates the inverter frequency and provides input to the DC link gain controller K3. A small voltage V0 added to the DC voltage reference to compensate for the stator resistance drop at the low frequency. The DC voltage VD acts as a reference for the voltage controller of the controlled rectifier. In case of a PWM inverter, there is no need for the controlled rectifier, and the signal VD controls the inverter voltage directly by varying the modulation index. For the current monitoring, it requires a sensor, which is introduced a delay in the system response. Since the torque of an induction motor is proportional to slip frequency, that is omega SL equals to omega S minus omega M, which equals to S omega S, the slip frequency instead of stator current can be controlled. The speed error generates the slip frequency command as shown in this figure, where the slip limits sets the torque limit. The function generator, which produces the command signal for voltage control in response to the frequency omega S, and is nonlinear and can take also into the account the compensation drop V0 at low frequencies. The compensating drop V0 as shown here. For a step change in the speed command, the motor accelerates or decelerates within the torque limit to steady state slip value corresponding to the load torque. This arrangement controls the torque indirectly within the speed control loop and does not require the current sensor is absent here. A simple arrangement for current control is as shown here. The speed error generates the reference signal for the DC link current. The slip frequency, that is omega SL equals to omega S minus omega M, is fixed. With a step speed command, the machine accelerates with a high current which is proportional to the torque. In the steady state, the motor current is low. However, the air gap flux fluctuates, and due to the varying flux at the different operating points, the performance of the drive is poor. A practical arrangement for current control with the flux is maintained constant is shown here. The speed error generates the slip frequency, which controls the inverter frequency and the DC link current source. The function generator produces the current command to maintain the air gap flux constant normally at the rated value. The arrangement for speed control with inner current control loop can be applied to the static KRAMERS drive as shown here, where the torque is proportional to the DC link current ID. The speed error generates the DC link current command. A step increase in the speed clamps the current to the maximum value and the motor accelerates at a constant torque which corresponds to the maximum current. A step decrease in the speed sets the current command to 0 and the motor decelerates due to the low torque. This is how the static KRAMERS works. The control methods that have been discussed so far provides satisfactory steady state performance, but their dynamic response is poor. An induction motor has a nonlinear multivariable highly coupled characteristics. Field-oriented control decouples the two components of the stator current. One provides the air gap flux and other provides the torque. It provides independent control of flux and torque, and the control characteristics is linearized. The stator currents are converted to fictitious synchronously rotating reference frame aligned with the flux vector and are transferred back to the stator frame before feeding back to the machine. The two components are D-axis, that is IDS analogous to armature current, and Q-axis, that is IQS analogous to the field current of a separately excited DC motor. The rotor flux linkage vector is aligned along the D-axis of the reference frame. The axis of reference rotation for various quantities is as shown here, where theta S is the stator phase A axis and theta R is the rotor phase A axis. Alpha to beta, that is stator fixed reference frame, and X to Y a rotor fixed reference frame, and D to Q is the synchronously rotating reference frame. The angle between X and alpha is theta R, D and alpha is theta S, whereas theta S minus theta R is nothing but theta SL. This type of control can be implemented by either direct method or indirect method. In the direct method, the flux vector is computed for the terminal quantities of the motor as shown in this figure. The indirect method uses motor slip frequency, that is omega SL, to compute the desired flux vector. It is simpler to implement than the direct method and is used increasingly in induction motor control. TD is the desired motor torque, omega R is the rotor flux linkage, tau R is the rotor time constant, and Lm is the mutual inductance. The amount of decoupling is dependent on the motor parameters unless the flux is measured directly. Without the exact knowledge of the motor parameters, an ideal decoupling is not possible. This is regarding the closed loop control of an induction motor with field orientation control. If this video is useful, please like, share and subscribe.